Hello, my name is Eric Severson, and I'm going to talk to you today about magnetic levitation for electric motors. But before I do that, I want to give you some background on myself and my research group. I joined the University of Wisconsin-Madison in the fall of 2017, and I was hired as part of the Grainger Institute for Engineering's hiring thrust in energy and sustainability. I'm an ECE faculty member and a part of Hvac. My research interests focus on electric motors, power electronics, and the control of motors and power electronics, which makes me feel right at home within the Hvac community. My research team, you can see on the right side of the slide here, has grown into a large and lively group over the past 3 years, and we take on projects anywhere within the core of Hvac's focus areas. So we tend to find ourselves working on electric motor design projects, and oftentimes these motor design projects feature weird or unconventional motors that need weird or unconventional power electronics, and then they need weird or unconventional control. And our twist on all of this is that a major thrust for us is on magnetic levitation. So that is getting rid of contact bearings and using magnetic forces to keep our motor shaft centered, as well as to rotate the motors. But not all of our projects do this, so sometimes we use bearings and sometimes we go bearingless. In today's tutorial, we're going to talk about the science behind levitating a motor. We're going to do a hands-on tutorial on how magnetic levitation works and how you can apply it to your own motor systems. So the outline of today's talk is as follows. We'll start by motivating magnetic levitation. We'll talk about the shortcomings of conventional bearings and how magnetic levitation can fit into today's motor systems and what opportunities it can create for tomorrow's motor systems. Then we'll talk about magnetic bearings, and we'll delve deep into the different topologies and the control of magnetic bearings. After that, we'll talk about bearingless motors, and similarly, we'll delve into the various topologies of bearingless motors, their control, and summarize some of our current research thrusts in this area. This tutorial is about motor bearings, or rather, it's about how to eliminate motor bearings from your motor system. And why do we want to eliminate motor bearings? Well, motor bearings are typically the first point of failure in a motor system. They're a source of major lifetime and reliability issues. They are also a source of losses in electric machines, particularly high-speed electric machines. And the lubricants that motor bearings use can cause problems within the broader system. So really we have these three reasons: reliability and lifetime issues, frictional loss issues, and lubricants causing problems within the broader application that a motor is used in. And I'm now going to present a couple example slides that highlight how these three shortcomings of motor bearings play out in a couple applications and that are ripe for disruption by magnetic levitation. The first example I want to talk about is that of a turbocharger for a vehicle. Turbochargers are devices that you can attach to the air intake of your vehicle to pressurize the air entering the internal combustion engine. They're used to allow engine downsizing, that is, to make it so you can create the same amount of power with a smaller engine, and to increase performance. Engine downsizing has been shown to enable decreases in fuel consumption by upwards of 10% in passenger vehicles. These turbochargers typically use journal bearings, and they operate at extremely high rotational speeds and at very high temperatures. You can see an example turbocharger on the right of your screen. The turbocharger consists of an expander wheel, which is in the flow of exhaust leaving the engine. That expander wheel spins a shaft, and on the other side you have a compressor wheel, which provides the pressurized air intake to the internal combustion engine. More recently, electric motors are being introduced into these devices to enable precise transient control and more effectively realize the benefits of improved engine efficiency and performance. The high temperatures caused by the exhaust and the need to spin at really high speeds to decrease the overall size represent very challenging environments for bearings. In fact, 80% of failures of turbochargers are due to failures in the bearing system. Frictional losses within the bearings cause a phenomenon known as turbo lag and can lead to significant efficiency reductions in the turbocharger. The turbo lag phenomenon is best explained by considering a vehicle that you've driven up to a stop sign. You're sitting at an idle condition and now it is time to get going. When you hit the accelerator, you'd like your vehicle to accelerate at a normal pace. However, due to turbo lag, your turbocharger has trouble spinning up from friction in the bearings, and this means that you don't get the power output from your engine that you would expect while you're waiting for your turbocharger to spin up. Third, oil contamination, that is, issues with lubricants in the bearings, can end up getting into the engine and causing increased emissions and smoke in the exhaust system. So the turbocharger example really hits on the three shortcomings of bearings. We've got reliability and lifetime issues, we've got frictional losses leading to undesirable performance, and we've got lubricants interfering with our broader system. The second example I want to talk to you about is in compressor systems for large HVAC systems. So I'm specifically talking about the kind of chillers that you'll see on the top of large buildings. For example, on this slide, I've shown a picture of the chiller that's on top of our WEI building on the UW campus. So these chillers are responsible for cooling water that is circulated into the building and is part of the cooling system for the building. And on the top, on the roof, where you have this chiller, you've got a motor that's driving a compressor. And in these systems, it's really important that you make this motor as efficient as possible. Every watt of loss in this motor ends up counting twice because it's a watt that ends up in your refrigerant and you have to remove it as part of the cooling process. And it's also important because these systems are really big. They can be upwards of a megawatt. And in total, HVAC represents about 17% of our energy consumption in the US. So in legacy systems, the motor will use lubricated journal bearings, and the lubricant is typically part of the refrigerant, and if the lubricant levels are off in the refrigerant, you end up having oil contaminating the heat transfer pipes in your HVAC system. So these are pipes that are used to exchange heat, and oil will build up in the little divots and crevices in here that are used to maximize surface area and actually impede thermal transfer. Trane published results from a study on this a few years back that showed how much efficiency loss you have in your building heating system as a function of the amount of oil that ends up in your refrigerant. So you can see if you've got, I don't know, if you've got 6% oil in your refrigerant, you have about 11% loss of efficiency in the building. And they then went out and surveyed their own commercial installations and found that their large systems typically had between 3 and 23% of oil in their refrigerant. So in fact, the lowest level of oil found in their refrigerant corresponded to a 5% efficiency reduction for the building's HVAC system. And the largest level is off this chart, right? It's somewhere out here in the 20 to 30% efficiency reduction range. So this is a great example of the lubricant of a bearing system interfering with a broader system. And for this reason, we've seen all of the major large HVAC manufacturers develop product lines that use magnetic bearings. So here's a typical example on the left of your screen, where we've got a high-speed permanent magnet synchronous motor that's suspended via magnetic bearings so that it requires no oil lubricant in the system. At this point, we've summarized two examples where conventional bearings have several noticeable shortcomings, and contact-free magnetic levitation offers a compelling value proposition. So let's now shift our focus to talking about the devices that are used to create magnetic levitation of a motor's shaft. The first of those devices are active magnetic bearings. Active magnetic bearings are advantageous over conventional bearings for reasons that you might expect. They're contact-free, which means that they're friction-free, and it also means that they're lubricant-free. And, perhaps for a reason that might be surprising, they have the ability to provide advanced health monitoring of your motor system. The reason for this is that active magnetic bearings require active feedback control. That means that they must constantly be sensing the shaft's position in the air gap of the motor. If new vibrations develop, this will be apparent to these sensors and can be relayed to an operator. This technology also has several challenges. Most notable amongst these challenges is that magnetic bearings have a low force density, much lower than conventional bearings. We'll talk more about that in a couple slides. Magnetic bearings can also be very difficult to integrate. For the same reason that we can do health monitoring, that is, that we have sensors, we now have a lot more components that must be mounted within the motor system and properly aligned. A lot of connections to make, a lot of wires to route. Finally, magnetic bearings have a propensity to have cross-coupling with the motor operation. So your motor essentially behaves as an unstable magnetic bearing. When your shaft is centered in the air gap, there's no forces on the motor, on the shaft, but the second that your shaft starts to deviate from the center, there's a large unbalanced magnetic force that's trying to pull it to the side. And this can excite resonances within your magnetic bearing controller, and you can end up with a shaft that has an orbit in the air gap of the machine, like we're showing on this slide. At the end of the day, a magnetic bearing looks an awful lot like a motor. It's got coils, it's got laminated stator core, it's got a laminated rotor structure, so you'd be forgiven if you saw this device and you thought it was a motor. The key difference is that instead of producing torque, it's producing either radial or axial forces. The second class of devices that we'll be talking about in this tutorial are bearingless motors. A bearingless motor, by definition, is an electric motor which can produce both torque and radial or axial forces. So that is, it uses its same steel, its same magnets, its same rotor bars if it's a squirrel cage induction motor, to produce both torque and radial or axial forces. And the general idea is that a bearingless motor can be used to replace one or more bearings, and it has the potential to solve many of the challenges of active magnetic bearings. We'll talk about this more later in the presentation. It turns out that you can design nearly any type of motor as a bearingless motor by simply adding a second winding to the stator that creates a suspension field. This suspension field interacts with the motor's field to create forces on the shaft. Let's now talk about how different bearing technologies can play out in large motor systems for industrial compressors. On the left side of the screen, I'm drawing the motor system that's been used to drive large compressors for well over a century. You can see that we've got the power grid directly connected to a very large motor. That motor is supported by journal bearings, which require a pump, a lubrication pump system to be attached. And then that motor drives a gearbox, which steps the shaft speed up to a high speed for a compressor. This system literally is the workhorse of the industry. It's very reliable. It simply works. You may have to have a maintenance plan to routinely swap out lubricant or change filters, but it works. More recently, systems have been developed like this, where we've got magnetic bearings that are supporting the shaft of a very high-speed motor, typically a permanent magnet motor. And because the motor is high speed, it can no longer be driven synchronously from the grid. Instead, we've got a variable speed motor drive connected in between. On the output of the motor is our compressor, but now you'll see that everything is drawn much smaller. This is intentional because the motor is spinning at a higher speed. It can be much more compact. We've got bearings, in fact magnetic bearings, that are used to levitate our shaft, and they require their own magnetic bearing control hardware. The magnetic bearing control hardware requires a battery backup system because if the power grid flickers, you don't want that shaft to drop down. So this system is becoming increasingly popular in applications such as HVAC or wastewater aeration equipment. Next, I'm going to summarize what we view as a future for magnetic levitated motors, which is the bearingless motor. So here you can see that we've got a lot of the same components as our mag bearing system. We've got a high-speed motor again, we've got a small high-speed compressor, we've got a variable speed motor drive, but we've just integrated everything very thoroughly. So now our radial bearings, the two blue radial bearings, are integrated into the bearingless motor housing. They are actually part of the bearingless motor. And the magnetic bearing is simply an axial bearing that's meant to support the shaft in the axial directions. So what we can say is that our first system, the legacy system, is mechanically complex but electrically simple. The magnetic bearing system is mechanically simple but electrically quite complex and has multiple points where electronics can fail. The bearingless motor system is mechanically simple and electrically simple. A couple slides ago, I stated that magnetic suspension has a lower force density than contact bearings. And we lay that out on this slide for you. So on the left side, we've got the typical force density of magnetic suspension technology. And on the right side, we've got the typical force density of a contact bearing. And you can see that we're comparing 10 to the 5 psi for contact bearing versus 100 to 200 psi for a magnetic bearing. The reason that the magnetic suspension force density is so much lower is due to the fundamental nature of how we're producing forces. Forces are produced by magnetic fields, and we're counting on steel to carry those magnetic fields. Well, this 100 to 200 psi is based on the amount of field that our steel can carry, the saturation flux density of our steel. So this is a fundamental limitation of the technology. However, you'll notice that it's not horribly misaligned with other bearing technologies. Airfoil bearings, for example, are in the 100 to 200 psi range as well. Hydrodynamic journal bearings are in the 250 to 300 psi range. So this certainly does not rule out magnetic bearings, but it does mean that you need to factor its low force density into your design of the motor system. And it can become problematic in some circumstances, such as really high-speed operation, where you're trying to minimize the axial length of your motor system to improve your rotor dynamics. So the bottom line here, the take-home message, is that in a magnetic levitation system, you only have so many newtons of force, and you must use them wisely. So we've talked about how magnetic levitation can inherently overcome the challenges associated with contact bearings. And we've also commented on some of the challenges with implementing magnetic suspension in a motor system, namely the low force density and the increased cost and complexity of the overall system. So when should you consider using magnetic suspension in one of your motor designs? Well, the answer is that you really should value some combination of the following items: frictionless operation, contact-free rotors, an oil-free system, long rotation life, variable rotor dynamics, low vibration, or health monitoring. I've put together a list of several manufacturers of magnetic suspension components. Most of these companies will sell you a set of magnetic bearings and a magnetic bearing controller that you can install in your motor design. A couple companies, namely Levitronics and Celeroton, focus on bearingless motors as well as magnetic bearings. In fact, Levitronics is the first company to commercialize bearingless motors, and they have developed them for hygienic pumping devices and artificial hearts. So their product offering is not a distinct magnetic bearing or a motor, but rather a finished product that incorporates magnetic levitation technology. At this point, we've concluded our introduction and motivation of why you should consider magnetic suspension for a motor design. Let's now delve deep into the technology. We'll start with magnetic bearings and later move on to bearingless motors. In magnetic bearings, we're going to begin by considering an in-depth study of how the technology functions. So roll up your sleeves and get ready to do some work. But before we go to magnetic levitation, we need to take a step back and talk about what we are trying to accomplish. And to do that, we're going to review the rigid body model of a rotor. So you can see on the screen here, I've drawn a motor shaft, and I'm going to label the 6 degrees of freedom of a motor shaft. The first degree of freedom I've already shown on here. That's rotation. That's what your motor is doing. Your magnetic bearings are responsible for supporting the remaining degrees of freedom. So your motor creates torque. It's responsible for spinning that shaft. Your magnetic bearing, or rather any bearing system, is responsible for supporting the remaining degrees of freedom. And those degrees of freedom are translation in the x direction, translation in the y direction, tilting about the x-axis, and tilting about the y-axis. My animation's a little exaggerated. Your shaft can't spin 360 degrees. It would hit the stator, right? But I think you get the idea. And the remaining degree of freedom is axial movement. So your motor controls rotation, and your bearings have to support these degrees of freedom 2 through 6, which are your translational movement in the x, y, and z direction, and then rotation about those axes, tilting motion. So keep this in mind as we talk about the rest of the tutorial. We're going to be talking about how to stabilize degrees of freedom 2 through 6. So we're specifically considering devices that can create forces along these directions. All right, here we are, the core of the material. So we're going to step through a few detailed slides here. And what we're going to do is we're going to build up from this relatively simple actuator that I'm drawing on the right to a complete 8-pole magnetic bearing. The 8-pole magnetic bearing is the standard magnetic bearing that you can buy today from a magnetic bearing manufacturer. It produces forces in the radial x and y direction. But to begin this, we're going to consider this system right here, which consists of an iron core on the top that has a coil wrapped around it, and an iron shaft beneath it. So if you excite this coil that's wrapped around this core with a current that I've labeled as I1, you can see it will create a field that follows this trajectory. That's the blue line. And in our analysis here, we're going to ignore the field everywhere except for in the air gap. And the air gap, or the air gaps are the two regions between our actuator core and our steel shaft. So that's this region right here, which I've labeled as G1 and G2. And if you go back to your undergraduate physics course, you'll maybe recall that you learned about something called a Maxwell stress tensor. The Maxwell stress tensor is a way to calculate force densities acting on the surface of a magnetic permeable object from the fields that are crossing that surface. So in this case, we can calculate this term TRR is a radial pressure force that's right here in our air gap as being proportional to the square of our radial field, that's the blue line, divided by 2 times mu naught. And mu naught is a physics constant, it's a permeability of free space. So that is to say we have a radial force density acting on this surface right here in this air gap, and a radial force density acting on the surface in this air gap. And if we use this Maxwell stress tensor, we can calculate the total force that is acting on our shaft. So we've got a force in gap 1 going radially outwards and a force in gap 2 going radially outwards. And we add those up and we get this term right here, which is saying that the force in the y direction of our shaft is going to be proportional to the square of our magnetic field times the area of that air gap, that's the area right here, divided by mu naught times the cosine of 22.5 degrees. And the 22.5 degrees is just the angle that each of these air gaps are relative to the y-axis. So that's great. But what we're trying to do here is build up a model that relates the force acting on our shaft to the current that we're flowing in our coil. And so what we need to do is we need to write our magnetic field in terms of the coil current, which we've done over here. If we plug this expression into our force expression, we end up with this new force expression down here. And you can see that we've got a force that depends on a bunch of geometric terms times the square of the current flowing into our coil. So we're going to group all these geometric terms into one constant. They're constant, right? As you're operating your magnetic bearing, they're not changing. They're always there. So we'll call that K. All these terms here are K. And so our force law says that we're going to have a force in the y direction that's equal to K times the square of our terminal current. So we're happy right now, right? We've created a model that relates the force on our shaft to the current flowing in our coil. Well, we're only mostly happy. This model says that we can only produce forces in the positive y direction, in the positive direction. We can't produce negative forces because if we were to flow a negative current, we'd still get a positive force. We're taking the square of our current. And also, we're not happy because this force law is nonlinear. We can see that our force depends on the square of current, which means it has this nonlinear dependence, and that is more difficult to implement a controller. So what do? Well, addressing the positive direction force capability only, we can add another core on the bottom side of our shaft, like as drawn here. So this core now has its own winding. So we've got two windings, and that means two terminal currents. Current I1 is on the top, current I2 is on the bottom. Both actuators have a coil of n turns, and we can then write out a force expression as the sum of the forces that these two actuators are producing. So that's great. We can now produce negative currents, or negative forces, but we still have a problem, which is that we've got an I squared term in there. So what we do is we decide that we're going to define our coil currents to have this form. That is, they're going to consist of a bias current, or a common mode current called IB, and a differential current called IY. So the top actuator has got our bias current plus our differential current. The bottom actuator has got the bias current minus the differential current. And so we haven't said why we're doing that, we're just doing that. But if we do that and we plug that into this force expression, you can see that we end up with the following control law. So we've just taken these currents, we've plugged them in up here, and we get out this force expression. Now our force is equal to 2 times our geometric constant times our bias current times IY. And if we decide that we're always going to flow the same bias current, we can just call this first term up here a constant called Ki, and we see that we now have a linear force model. Force is equal to Ki times Iy. And we're happy. We can now produce both positive and negative forces. If you want a negative force, you just flow a negative Iy. And we have a linear dependence. There's no longer a square term in our control current dependency. So that's great. However, this model is still not complete. If you were to take this model at face value, it would tell you that when you're flowing 0 control current, you will never have a force on the shaft. However, we know that's not true. We know that if we have our bias current flowing and we displace our shaft upwards so that it's closer, so that the air gap on this side is smaller than the air gap on this side, we're going to have an attractive force which will cause the shaft to pull into our top core. We know that from playing with magnets as a kid. If you get your magnet close to a piece of steel, it wants to pull in, right? So what do we need to do to make that? The answer is that we revise our force model. So if we model our air gap as having a differential length y based on how much the shaft has been displaced, we can rewrite our expression for fields in the air gap as follows. And if we plug that expression for fields into our force law, we get out the following expression. The first half of our expression is the same as we originally had for our magnetic bearing. That is, we have our geometric constant times I1 squared minus I2 squared. The second term is new. It's got I1 squared plus I2 squared, and then that quantity is multiplied by the amount of displacement we had in the y direction. So what we do to simplify this is we take the same approximations as we did before for this. We have a bias current and we group this into a constant and a control term. And then on the right side, we decide that we're going to take this first portion of the expression as being a constant that we evaluate at our bias current. That is, we evaluate this term and call it K delta. We evaluate it when I1 equals I2 is equal to I bias. That means we have no control current flowing. So if we do that, we get finally our linearized force model, which is that our force is equal to a current constant, Ki, times our control current, plus a displacement constant, K delta, times our displacement. And this is the complete linearized control law that's used to design controllers for magnetic bearings. Okay, so we're now ready to talk about the 8-pole magnetic bearing. You can see that up until this point, we've been talking about an actuator up here and an actuator down here. That system was able to actuate forces in the positive and negative y direction. To actuate forces in the positive and negative x direction, we simply clone that and rotate it 90 degrees. So now we've introduced a new actuator over here and an actuator over here. And for ease of manufacturing, we can connect the whole thing with a common yoke. And this is the conventional magnetic bearing that you can buy today from magnetic bearing manufacturers. It produces forces in the radial x and y direction. Notice that we've cleverly arranged our poles to have this pattern of north, south, south, north, north, south, south, north. And we did this so that when our shaft is rotating, it sees less alternations of the magnetic field direction. This decreases the losses in the system. It's a trick you can play with a magnetic bearing that you can't play with a motor. Finally, I want to point out that when you build a system like this, you're going to laminate your steel just like you would a motor. So this really looks like a stator of a motor. We've got stator teeth with coils wrapped around them, and then we've got a rotor structure in the center, and you'll also laminate the surface of that rotor structure so that the field path for your magnetic suspension field consists of fully laminated steel. The reason that you want to do this is to avoid eddy currents that would have a dampening effect on your magnetic performance. So if you tried to use solid steel, you'd find that your control law actually has a pole in it, and you're not able to regulate high frequency forces. Okay, so we built up to the conventional radial magnetic bearing. Let's now talk about the axial magnetic bearing, and then launch into a couple of other topology variants. So the axial magnetic bearing works on much the same principles as the radial magnetic bearing. That is, we have this desired control law here, which says that we're going to produce force in the z direction, that is the axial direction of our shaft, and it's going to be proportional to some coil current plus the displacement we have in the z direction. So that's the goal. How do we actually do this? Well, you can see the structure that I've drawn here. We've got our shaft, and then we've got a disc on the shaft that comes out. And we've got a coil on either side of that disc that wraps around the shaft. And then we provide a flux path for field to flow from that coil. So as I've drawn up here, you can see that we have the following blue flux path when we flow a current in that coil, in those two coils. And just like the radial bearing, we're trying to enhance the field on one side and weaken it on the other side in order to create a force. So it's the exact same principles, it's just now that we're talking about fields flowing in the axial direction. In this bearing structure, you can't really laminate the steel. You've got a 3D flux path essentially, right? And so what you end up seeing is that these bearings typically have a lower force bandwidth than the radial bearing counterparts. It's one of the known limitations in axial magnetic bearing technology that's starting to get re-examined in light of advanced manufacturing techniques. Another topology variant of the radial bearing is a homopolar bearing. So this bearing is used to produce radial forces in the x and y direction, not axial forces, but radial forces. But instead of using a bias current, it uses bias permanent magnets. So you can see here, I'm showing a 3D cross-section of a machine, and I've got a permanent magnet installed between two radial cross-sections. So if I've got, these are radial laminations up here like we would have for the 8-pole bearing, and then they're sandwiching this permanent magnet that's creating a field in the axial direction. So the axial flux path takes the blue line here, and then I've got an air gap up here in this radial stage, right? I've got an air gap over here in the radial stage, and that we're going to try to enhance or weaken the fields with control coils. So this permanent magnet field acts like a bias field. We can now switch to the right cross section, and the blue permanent magnet field appears to have a monopole or a homopole in the center of the shaft and is coming out from the center radially in all directions. Our control coil's purpose now is to enhance or weaken that field in order to create a force in the x and the y direction. So this ends up giving you the same control law that you had for the other bearing structures, which is that you've got a force term that's proportional to your control current and a force term that's proportional to your displacement. But the key difference is that this control current is actually the total current that's flowing in these coils. And because of this, because of the fact that you don't have to flow a bias current, you can actually connect these coils in series and use a single full bridge converter to operate them. whereas in the 8-pole radial bearing you had to use separate converters for each coil. This also ends up giving you lower loss because you don't have an alternating magnetic field. If you're not producing any forces on your shaft, you see that you have a constant magnetic field at all locations as your shaft rotates. But of course, it's a more complicated structure to manufacture, and you potentially have unused space within the cross-section of the machine here where your permanent magnet has to be sandwiched. Next, let's talk about another common topology variant, which is the combined radial axial magnetic bearing. So this magnetic bearing is able to produce both radial and axial forces. So that is, we have two force laws, one for forces in the radial cross-section and another for forces on the axial direction of the shaft. And this works very similar to a homopolar bearing. It's just that we've now replaced one of the radial force-producing sections with an axial force-producing section. So again, we've got an axial-facing permanent magnet that creates a bias field. And we've got a radial stage up here that's got 4 poles on it that is used for producing radial forces. But in our second radial stage has been replaced with the conventional axial stage with a key difference. We now need only one coil for that axial stage because we're able to interact with the permanent magnet flux. We've now summarized the most common topology variations of active magnetic bearings. Other topologies do exist, for example 3-pole bearings or 4-pole heteropolar bearings, but these topology variants can be quickly understood based on the fundamental principles that we introduced in the preceding section. I'm now going to turn our attention to the control approach to magnetic bearings, and we're going to start at a high level. If you refer to the right side of your screen, you can see I've sketched again our simple shaft with an actuator on the top. And I want you to pretend that we also have an actuator on the bottom. I'm just, for simplicity, drawing it this way so that in the bottom I can locate a position sensor. So our goal is to keep this shaft in the center between the two actuators. And so to do that, we're going to first measure the position of our shaft, and we're going to feed that into a regulator. We want to have our shaft have 0 displacement. So this is in the y direction. We want y to be 0. Remember, y was our displacement from the center position. We're going to feed any error of that into our position regulator, and that regulator is going to give us a force command which will go into our current regulator to be injected into this coil. So force, we just divide it by that Ki term from our linear model. So here I've written out our linear model when we've got 0 displacement. So if we divide force by Ki, we end up getting our control current. We add to our control current our bias current, and that gives us a reference for how much current should be in the coils of this bearing. So we compare that reference to a measurement of the actual coil of that bearing, and that gives us an error that we can feed into our current regulator, which gives us a voltage reference for what voltage we should be applying to our coil. We then use power electronics to pulse width modulate a voltage that we apply to this coil. So this uses what should be a familiar control structure to that of motors. We've got an outer loop, which is our position regulator, and then we've got an inner loop, which is our current regulator. Let's now talk about some of the details of these loops. First, let's start by deriving the transfer function for our position regulator. And if we go back to the fundamental linear force model that we developed, we've got our force equal to our force current constant times our control current plus our displacement constant times our displacement. We're going to replace this first term here by just saying that that is the force that our controller is able to actuate on the magnetic bearing. We'll call this FCY. This is how much force we can command to our current regulator and produce on the shaft. So if we then use the equation of motion, that is mass times acceleration is equal to force on the object, we can derive a transfer function. So mass times acceleration is equal to the force that we're able to produce on the shaft with our controller plus our unbalanced pull. And if we take this to the Laplace domain and write it out as a transfer function, we see that we end up with an unstable pull. We have a pull in the right half plane. And so this is not a surprise. We know that we expect the system to be unstable because intuitively you know that you can set the shaft in the center between these two actuators, and you can find a place in the center so that it doesn't pull to either side. But the second that you displace that shaft from the center, you're going to have an attractive force to one side or the other. That is, the center of your air gap is an unstable equilibrium point, and any displacement from there will cause the system to go unstable, to pull all the way to the side until it crashes. So our job is first to design a controller that's going to stabilize the system, and then second to design a controller to meet some kind of performance specification that we have. And so it turns out that perhaps the simplest and most intuitive way to design your controller is to visualize the system as a spring mass damper. This is kind of the classical formulation for any mechanical engineering analysis of a bearing system or of a mechanical system. And so I've drawn out what a spring mass damper looks like. So here's our mass, that would be our shaft. And if we excite this, we're going to say that we've got some stiffness that's going to oppose any movement of this mass, of our shaft, as well as some dampening that's going to oppose the velocity of that movement. And so we end up with this differential equation for a spring mass damper system. M times our acceleration is equal to a stabilizing stiffness times our displacement, and then subtracted with a dampening force. And so we can make our system look like this. And we do that, so here's our differential equation for our system, and we do that by modifying our control law in this differential equation to have this form. And so if you look at this, if you plug this control law, if you plug this force, if you plug this actuator force into our differential equation and solve it, you're going to get out the spring mass damper system. So this is great. From a user perspective, you can say, hey, I want my magnetic bearing to have a certain stiffness Ks and a certain dampening Kd, and now you know how to control the force that is going into your magnetic bearing. That is, you know what gain should be multiplied by any displacement and what gain should be multiplied by the derivative of the displacement. Well, look, this happens to be a PD controller. We've got a proportional term here, which is Ks plus K delta, and a derivative gain here, which is the dampening that we desire. And so this is a classic controller form, a proportional differential controller. And so we can replace that position controller block on our previous slide as this right here. So that's great. In practical systems, we typically use more complex controllers. A slightly more complex version of this is to introduce an integral term to eliminate any steady state error. And we can get more complicated from that. We can actually schedule our gains so that we can tune them based on the speed that our shaft is spinning and actually vary the stiffening and dampening of our system in real time to compensate or avoid resonances and critical speeds. So this is part of one of the advantages of magnetic levitation is that your spring mass damper system becomes completely programmable. You can modify it on the fly in response to real-world circumstances. I now want to conclude our magnetic bearing unit by, again, summarizing the opportunities and challenges of magnetic bearings. So as we talked about at the beginning of this section, the key advantages of magnetic bearings over contact-type bearings are the contact-free operation that can lead to high efficiency and long lifetime. The fact that these magnetically levitated systems are highly sensorized enables them to be used for advanced health monitoring. They have tunable rotor dynamics, which can be used to eliminate vibration and create quiet operating conditions. They're oil-free, which means that they have no maintenance requirements, and they avoid contamination challenges of lubricated bearing systems. However, they're not without their challenges and shortcomings. Most of the challenges can stem from their low force density and the requirement for long axial length. In addition to the force density limitations we talked about in the beginning, magnetic bearings also need to factor in additional space for sensors and end winding connections. This reduces the amount of space available for a motor and is particularly challenging for really high speed systems. On the bottom here, I sketched out what one might imagine a turbocharger concept to look like if it's levitated by magnetic bearings. You can see on either end we've got radial magnetic bearings sandwiching an axial magnetic bearing. At really high speeds, your shaft length is limited by rotor dynamic considerations, And in this type of system, there really isn't any room left to add an electric motor. So in theory, you could make your turbocharger be magnetically levitated, but you wouldn't have space to make it be an electric turbocharger and have a motor on the shaft. Another challenge and shortcoming of magnetic bearings is additional power electronics and sensors that are required tend to add more expense and bulk to the system and be difficult to integrate. And then finally, magnetic bearings require touchdown bearings to catch the shaft in case of a failure. These touchdown bearings have to be replaced if they're used frequently. So that's one of the reasons that you see magnetic bearings oftentimes implement a battery backup system. And finally, we mentioned the potential issue of cross-coupling with the motor. Now we're going to move on to talk about bearingless motors. We're again going to start with different topologies and the control approach, and then we're going to move on to talk about some of the current research directions in bearingless motors. So, as you recall, a bearingless motor is a single machine that produces both torque and magnetic bearing forces. Its purpose is to replace one or more bearings, and basically you can understand a bearingless motor's suspension operation as it uses the magnetizing field of the motor in place of the bias field of a magnetic bearing. So remember, a magnetic bearing required a bias field and then a control field. We talked about a bias current and a control current. Well, in a bearingless motor, we use the motor's field as the bias field, and then we add a new field to the motor that acts as the control field. Bearingless motors have potentials to solve most of the challenges of magnetic bearings. Because they use the same hardware as the motor, they can reduce cost tremendously. They inherently have a lot of oversize built into them. So magnetic bearings, you have to oversize them to handle emergency conditions. In a bearingless motor, typically the torque requirements of your motor inherently make the motor oversized. You don't have to pay for extra material. And you get better space utilization, and they give you a more integrated solution. So while we said that you couldn't fit a motor plus magnetic bearings onto a turbocharger, you could fit, potentially, a bearingless motor plus a magnetic bearing onto an e-turbocharger. And this is something that my research team has been thinking about. So before we get too far into this, I want to back up a step and just give an example of a hypothetical bearingless motor and the forces that are produced on it. So this is an example from a textbook here. And in this example, we've got an imaginary motor that's got 4 stator teeth. It's got a 2-pole rotor. And what we're going to do, we've got some example dimensions up here, and we assume a mass density of the shaft. What we're going to do is we're going to calculate the fields that are produced on that shaft from the forces that are produced on that shaft from an air gap field of 0.7 Tesla. And so we can go back to our Maxwell stress tensor, assume this air gap field, and we can find out that we're creating 255 newtons of force that happen to be equal and opposite on our shaft. So our shaft has no net force, but under each of the stator teeth there are 255 newtons of force pulling radially outward. And in this case, if we were to calculate the mass of our shaft, we find that it actually corresponds to a weight of only 7.3 newtons. So inherent to this motor, under no load conditions, we see that we're producing 35 times the rotor weight under each stator tooth. It's just that this force happens to cancel out, so there's no net force in the rotor. But clearly the motor has a tremendous force producing capability. It's just not using it. It's not using its newtons very wisely, one might say. So the idea of a bearingless motor is to disrupt the symmetry in the air gap by adding an additional field so that we create a net force on the shaft. And so in this example, we can see that in order to support the shaft's weight, we have to add only a 5 millitesla field to the motor's field. So the motor no load air gap field is 0.7 Tesla. If we add 5 milliteslas to it on the top, and we take 5 milliteslas off on the bottom, we produce 7.3 newtons of force on the rotor, and that's enough to fight gravity. So you can see in this example that we have a tremendous untapped force potential in our bearingless motor. And the whole idea of bearingless motor technology is to use the inherent force producing capability of the motor to make it be its own magnetic bearing. Bearingless motors can be categorized into different topologies based on the number of degrees of freedom that they are actively able to support. I've shown 3 categories here: a 2 degree of freedom, 4 degree of freedom, and 5 degree of freedom system. In these cases, I'm not counting torque as a degree of freedom. So let's look at the 2 degree of freedom system. Here we've got our bearingless motor in blue, and it's able to produce forces in the X and the Y direction, as well as torque. But I say it has 2 degrees of freedom because it produces X degree of freedom forces and Y degree of freedom forces. In this case, the bearingless motor relies on external support for the remaining degrees of freedom. I've drawn it as a combined radial axial magnetic bearing in green, but this could be an airfoil bearing or a needle bearing or some other type of bearing. Another variant on this system is sketched below, which I'm going to talk about a little bit later. And in that case, passive magnetic bearing forces are used to support the remaining degrees of freedom. In the middle, we've got a 4 degree of freedom bearingless motor system, where we actually have implemented this with two degree of freedom bearingless motors, and then an axial magnetic bearing in the center. There are other types of bearingless motors that inherently can produce 4 degrees of freedom. For example, the AC homopolar motor. On the right, I've shown a 5 degree of freedom bearingless motor system. This is an emerging technology that has not seen much development, but it's something that we're working on in our research group. In this case, you can have a cone-shaped air gap so that you can control field weakening of the motor on both sides. So here we've got one motor, and here we have a second motor. If we control field weakening, we can produce axial forces, and then we can control our normal forces to control tilt and radial movement. Bearingless slice motors are a common and successful type of 2 degree of freedom bearingless motor systems. This is the category that I commented earlier is able to use passive magnetic forces to stabilize the remaining degrees of freedom. In these types of bearingless motors, we have a very short axial length of our rotor relative to the diameter of the rotor. If we do this, we can rely on fringing fields to produce stabilizing forces in the axial direction. So here's our stator, here's a rotor, and you can see that as we try to pull this rotor down out of the stator, it's going to want to pull back up, right? Or similarly, if we try to tilt this rotor within the stator, it's going to try to correct itself and tilt back to a parallel path. This type of system is unstable in the radial direction, so your rotor will want to pull into one side or the other. And to correct that, you use bearingless motor forces as a 2 degree of freedom system to produce X and Y direction forces and keep it centered. So these motors have been developed for low power ratings over a broad speed range. And they've been commercialized by Levitronics for hygienic pumps and artificial hearts. Let's now talk about the basic principles for how force is created in a bearingless motor. I've drawn on this slide on the right side a 4-pole magnetic bearing. In the center is our rotor with permanent magnets on it, and outside of that is our stator. We can see that we've got many teeth with slots that will hold our winding. And just as we talked about in our previous example, this rotor right now has no net force on it because it has symmetry. So remember that force is produced by the square of our magnetic field in the air gap. So we can see that under this north pole here, we're going to have force that's pulling the rotor to the right. But under this north pole on the left side, we have force that's pulling the rotor to the left. And these forces are equal and opposite and cancel out. We say that this motor has 4 poles or 2 pole pairs. The number of pole pairs is an important concept for later slides. So let's talk about what it means now. A pole pair is a pair of magnetic poles because magnetic poles come in pairs. So we've got a north pole here and its corresponding south pole is counterclockwise to it. So this is 1 pole pair or 2 poles. So this rotor has 4 poles or 2 pole pairs. And it turns out to disrupt the symmetry on the rotor and to create a net force in a radial direction, we need to introduce a new field in the air gap of our motor that has a different number of pole pairs. In fact, the new field must differ in the number of pole pairs by 1. So either 1 pole pair more or 1 pole pair less. In this motor, where we've got 2 pole pairs, we could add either a 1 pole pair field or a 3 pole pair field to produce a net force. Let's consider the case of a one-pole pair field. So here I've drawn a two-pole winding, or a one-pole pair winding in blue, and its corresponding field lines. And you can see that the field lines enhance the air gap field on the right. It's going the same direction as the magnets. And on the left, they cancel the air gap field. So what we're left with is a net force produced to the right. And at this point, it's helpful to point out our degrees of freedom, or what we can control about the system. I've drawn this single phase winding that produces the field as shown in blue. And the only thing we can do with it is change the magnitude of current in that winding. So we're able to produce a force vector in the x direction, and the magnitude and direction of it depends on the amount of current we flow in that winding. However, if this rotor were to rotate, we would no longer be producing a field in the right direction, but we might be producing a field in the left direction because now our south poles would be lined up. So what we do is we use a multi-phase winding so that we can produce a field in any arbitrary location in our air gap, just like we do for torque creation, only now we do it for creating radial forces. So here we have the case of a three-phase winding, and we can control our three-phase fields to produce a force in any arbitrary x and y direction on our shaft. We can see from this that we need our winding to create two different fields in the air gap of our motor. One field is the normal field that we always have in an electric motor, and that has the same number of pole pairs as our rotor and is used to create torque. The second field, our suspension field, will have the plus or minus one pole pairs we've just been discussing, and that will be used to create the suspension forces. Traditionally, bearingless motors have used two different windings for these purposes. One winding is your standard motor winding. This is the same winding that you'll find in any motor, and it creates your P pole pair field. It will connect to a standard motor inverter that can be operated with standard control techniques. It's just a normal motor winding with a normal motor phase characteristic. The second winding will have the same number of phases, but will now be connected to a distinct separate inverter and will be used for creating that suspension field. And so these two windings share the same slot space. So that is, you could have a single layer torque winding and a single layer suspension winding, and then you'd say that your complete motor system has got two coil sides in each slot, one coil side allocated to torque and one coil side allocated to suspension. From a control perspective, the motor winding is again exactly the same as you would have in any motor, while the suspension winding is viewed a little bit differently. So if you see here, I've got a force expression for the forces that are produced on the shaft of our motor. This is the same linear force expression that we developed for the magnetic bearing, except for now it's a vector. That's because it contains information about the x and y direction forces. Those forces can be understood again as a linear dependence on the suspension currents and a linear dependence on the displacement of the shaft in the air gap. The suspension currents can be described by a current space vector. Those of you familiar with motor control will understand how to construct a current space vector from your three-phase currents. The relation between the current space vector and the forces that are produced in the shaft are described by this complex quantity Ki. Ki is complex quantity. It's got a magnitude and a phase angle. The magnitude is familiar. That's going to map amperes of current to newtons of force. And the phase angle, the angle of Ki, depends on the type of bearingless motor you're creating. We're not going to go into much depth on this, but I want to mention it briefly that there are two categories of bearingless motors. The first category is what we talked about on the previous slide. It's called a P plus or minus 1 because that's how many pole pairs your suspension field has relative to your motor field. The second category of bearingless motors is called a PS equals 1 motor, and that is bearingless versions of the AC homopolar or consequent pole motors. The difference between these two motor types is whether the angle of Ki is constant or whether it depends on the rotor angle. So you can see that the first type of bearingless motor depends on the rotor angle. This means that your suspension space vector, your suspension current space vector, is going to have to rotate at the same speed as your torque current space vector. So in other words, in the P plus or minus 1 type of bearingless motor, your suspension currents are going to be sinusoidal with the same excitation frequency as your motor currents. Here I'm showing you the control structure for a bearingless motor. Let's unpack this a bit. Here's our bearingless machine, and on this side of the machine are our three-phase connections for producing torque. On this side of the machine are our three-phase connections for producing suspension forces. So let's start with the torque connections, because we're all more familiar with creating torque in an electric motor. So in this green dashed box up here, I've drawn our conventional field-oriented motor control structure. We've got some D and Q reference current that are going to a PI-based motor controller and used to create voltage references for our power electronics that are then applied here. So that is the conventional approach that we take for field-oriented control of an electric motor. Now the suspension path. So the suspension's path, if we start on the left side, it begins with a reference for X and Y position in the air gap. And remember, these are typically just 0. And it feeds that into the PID-based suspension controller that we talked about for magnetic bearings. This is the same controller that we talked about in the magnetic bearing unit. That generates X and Y force references that should be applied to our shaft. And from that, we determine what the X and Y current components are of our suspension current space vector. We do that by solving the linear force law that I presented on the previous slide, where we've got our Ki constant with a magnitude and an angle. These currents are then regulated to apply voltages to the terminals of our suspension winding. We've now concluded the tutorial sections on the fundamental topologies of bearingless motors and the control approach for bearingless motors. And we're going to delve into the current challenges with bearingless motor technology and research initiatives to overcome these challenges. First, we'll discuss the challenge of separated windings. We talked earlier about the fact that you need two magnetic fields in the air gap of a bearingless motor. One field to create torque and a second field to create suspension forces. And we noted that traditionally, bearingless motors use two different windings to create these fields, a torque winding and a suspension winding. These two windings are installed in the same stator slots, which means that they compete for slot space. Any amount of space that you allocate to the suspension winding is no longer available to the torque winding. And it turns out that you typically have to allocate upwards of 25 to 50% of the slot space to the levitation winding so that you can produce enough force in case of an emergency. This derates the torque rating or the power density of your motor by 25 to 50%, and also results in longer and deeper slots that create longer flux paths in the steel, resulting in more iron loss, and creates more conduction loss. So we can see here's a cross-section of a bearingless motor that's been water jetted, and we can see that we've got our drive winding here, and our suspension winding is sitting in the front of the slot space, occupying approximately 30% in this example motor. In addition to that, motor systems with two separate windings are more expensive to manufacture. So the net result is that legacy versions of bearingless motor technology are simply inferior motors compared to a non-bearingless motor. So they might offer the value proposition of magnetic levitation, but you pay a penalty in terms of the motor performance. This observation is made more bittersweet by realizing that during normal operating conditions, only 2.5% of the slot space is required for the suspension winding, and 97.5% of the slot space could be used for the torque winding. However, we have to size this not for normal operating conditions, but for worst case scenarios. And the worst case scenario is what drives us to the 25 to 50% of the slot space being allocated to the suspension winding. So we must design for this point down here, but then under typical operating conditions, we just sit up here, except for maybe when we're passing through a critical speed or we're handling a compressor surge event. So for this reason, one of the major research thrusts in bearingless motors these days is in developing a combined winding. The idea of a combined winding is to use the same coils for levitation forces and torque creation. There are many different approaches to implementing a combined winding. I've given a few citations below for different research groups. Our research group is developing a type of combined winding that we call the no voltage winding, or the dual purpose no voltage winding, and it has certain advantages. It's able to use a standard motor drive for motor operation. This is great because in an industrial application where you've got high motor power, you don't really want to be messing around with custom power electronics in the main power path. It also doesn't expose the suspension current path to any back EMF. This reduces the volt ampere rating of your suspension inverter. We'll talk about that more in a few slides. First, let's frame what we're trying to accomplish here by using a combined winding. We're trying to solve the performance challenges of traditional bearingless motor technology that uses separate torque and suspension windings. That is, we're trying to increase the torque density and efficiency of a bearingless motor to be the same value that we're able to design into high performance motors that use contact bearings. And we found that using a combined winding actually does solve these challenges. We're able to get about a 40% increase in torque density in both permanent magnet motors and induction motors that use combined windings as compared to those that use separated windings. You can see in the plot on the right here, we're showing many different designs. Each marker indicates a different motor design, either an induction motor with a combined winding, an induction motor with a separated winding, a permanent magnet motor with a combined winding, or a permanent magnet motor with a separated winding. And the combined windings always come out as being more torque dense and more efficient than the separated windings. So this is an area of active research. And now let's delve into how combined windings function. The combined winding must create two fields in the air gap of the machine. One field needs to have P pole pairs to create torque, and the second field needs to have PS pole pairs to create suspension forces. Remember, PS is either equal to P plus 1 or P minus 1. So the question you should be asking right now is, how the heck can one winding create two independent fields? So I'm going to step through this now with a simple example. We're going to consider a 4-pole motor with a 12-slot stator and a 3-phase winding. And this is kind of an arbitrarily simple winding example and structure, but bear with me, it explains the concept with good clarity. So you can see I've laid out the 3-phase winding in the slots. I'm indicating the coil size that are in each slot. And so you can see we've got phase U, V, and W. And down below, I'm drawing the MMF from phase U. And it's a 4-pole MMF, which you'd expect because it's a 4-pole rotor. So we've got a north pole, south pole, north pole, south pole. On the right, I'm about to unveil the same stator winding, but now half of the coil sides have been reversed in direction. So you can see in slot 1, the top coil side is now in the opposite direction as it was from the torque excitation. And what this does is it produces a 2-pole field in our air gap. So now our phase U MMF has got a north pole and a south pole. So the key thing to take away from here is that we've been able to change the number of poles in our air gap by reversing half of the coil side's direction. And so the next step, the next slide I'm going to show you, is going to show how you can connect that to a motor drive to accomplish this goal of having one direction of current in the coils for torque production, and then half the coil sides carrying current in a different direction for suspension excitation. Okay, so the drive connections, it turns out that there's two ways of doing this. The first is called a bridge configuration, and we'll talk through that, and then we'll show you the second way, which is a parallel configuration. So in the bridge configuration, we take our stator winding and we've designed it very deliberately so we're able to do this. And one of the keys is that we have to have 4 coil groups per phase. So we place our coil groups into bridge configurations where in the center of each bridge we've got an inverter. And outside of our 3 bridges, we've got our motor inverter. So the motor inverter is just a standard motor inverter. It doesn't know anything about this being a bearingless motor winding. All it cares about is that it sees a parallel path to a neutral point. The suspension inverter is in the center of these bridges, and you can see that when it injects a current, it's going to take this pink path, and it will flow in the same direction as the motor current in half the coil groups. So in coil group B and D, it's in the same direction as the motor current, but in coil group A and C, it's in the opposite direction. And so now we've accomplished what we wanted to do. We've reversed the current direction in half of the coil groups by using this bridge configuration. And so it has the same force relationship as we had talked about for the separated winding. That is, we can talk about the phase currents of the suspension inverter in the center here and construct a current space vector that maps to our forces. And so that's the bridge configuration. the parallel configuration is intended for the exact same winding design, but now we connect our coil groups as is shown in this figure, where we've got our motor inverter, which is again a three-phase motor inverter and does not need to know that this is a bearingless motor. And the motor inverter sees a physical neutral point that half of its current will flow to, but then it sees a virtual neutral point. In fact, this point here, if we were to short circuit it to the corresponding points on the other phases, it would just look like a motor with two neutral points. But instead of having that second neutral point, we open it up and we attach a new inverter. And this new inverter is a suspension inverter, and it will superimpose a current on top of the motor current that will do the same thing that our bridge configuration did. That is, that current takes the opposite direction in coil groups A and C, but the same direction as the motor current in coil groups B and D. And so it's able to produce, again, suspension forces in the same manner and using the same force relationship. Now, one other thing I want you to take away from this is that from our suspension inverter perspective in both designs, we do not have any back EMF in the motor. So each of these coil groups is this equivalent circuit here. It's got a back EMF, it's got some inductance and some resistance, and so the dots indicate the polarity. From the motor perspective, you can see that here's our neutral point. The dots add up, so our back EMF adds up, and we see the back EMF from the motor inverter perspective. This is necessary for producing torque. From the suspension inverter perspective, however, the dots cancel. So if we start from here, we have a positive back EMF, and now we have a negative back EMF, so therefore we have no back EMF across here. This is an important property of these windings, and is in fact where the name no voltage comes from. By canceling out the back EMF from the suspension perspective, we're able to reduce the volt-ampere rating of our suspension inverter. Typically, the suspension controller needs to be designed for a much higher bandwidth than our position regulator, than our motion regulator, our rotary motion regulator. And so if we're able to avoid having to overcome the back EMF, we can reduce the voltage rating of our voltage bus. Okay, so in a whirlwind, that's how these motors, that's how this winding structure works and how they're able to be operated from power electronics. Let's now talk about how we actually implement the power electronics. And I'm going to start by just commenting on the regular old traditional bearingless motor approach. So again, from our previous slide, we had talked about how we've got two separate windings and two separate inverters. The simplest approach is to implement each of these as three-phase voltage source inverters. And from that, you can tally up how many switches are required, how many current sensors, and so on. Well, it turns out that when you go to these combined windings, the motor design is substantially improved, but your power electronics pay a penalty. And I'm not really going to talk through this other than to say that there's been a lot of research from us as well as other groups on different ways of implementing your power electronics to try to minimize the power electronic penalty. The other thing I want to comment on is we've talked about how the combined no voltage windings work and how the power electronics are implemented. Well, it turns out that you also have to pay a lot of attention to how you design the winding in order to have these properties, in order to have the no voltage property, in order to produce a symmetric field in the air gap, and this is non-trivial. It turns out that only certain combinations of stator slots, rotor poles, and winding phases can work to create a dual-purpose no-voltage winding. Thankfully, it turns out that most common motor windings can be turned into dual-purpose no-voltage windings by simply bringing out the end connections of the motor and attaching your suspension inverter to a select combination of end connections. And this is something that we've been thinking about in our research as well. I wanted to walk you through just very briefly what the design process looks like for constructing a no-voltage winding. And the first step in the design process is that you use a lookup table to figure out if your combination of slots, poles, and phases can in fact be used to create a no-voltage winding. The second step is that you follow a sequence of steps actually to lay out the winding. So first you'd use the conventional means to lay out a torque winding. Here I'm showing it for the star of slots approach. We've got phase bands and we're grouping our coil sides, our slots based on phase bands to determine what phase they belong to. And a second step is you redraw that star of slots at the suspension windings frequency, and you select half of the phasers or half of the coils that you're going to reverse in connection for creating the suspension field. And then when you draw out those phasors, you're able to identify which coil sides should be placed into each of these coil groups so that you cancel out the motor's back EMF. And finally, you can construct your winding schematic for your motor winding. So in conclusion, the combined winding bearingless motor has the potential to solve several challenges of magnetic bearings. It has this highly dynamic torque versus suspension force capability. In fact, you can stop thinking about the motor as being a torque producer and start thinking about it as a machine that produces a magnetic stress on the surface of the rotor. And by using this combined winding approach, you can control how much of that stress is in the tangential direction for creating force and how much of that stress is in the radial direction for creating forces. And so based on your operating conditions in real time, you can move your motor's stress capability to creating torque or to creating forces. It becomes a very dynamic force producing device. This is a highly integrated solution. It avoids resonances with motor operation because you're controlling the forces right at the point of where they are created. So there's not, in a magnetic bearing, you're creating forces at one location on the shaft where the magnetic bearing is, and then you can create forces also where the motor is accidentally if your rotor becomes displaced. So bearingless motors if we back up and look at the grand scheme of magnetic suspension technology, magnetic bearings are fairly mature. They're commercial products. You can go buy off-the-shelf components right now. Bearingless motors are rapidly maturing. They're commercialized for niche applications where you don't care about performance, but we've been showing that you can, with today's technology, if you employ good design practices, you can design these machines for high performance applications as well. So we've now concluded our 3 main thrusts in this tutorial. For more information, I would refer you to these publications. For magnetic bearings, there's a well-known book published in 2009 by these authors. For bearingless motors, there's another well-known book out of Tokyo Institute of Technology, published in 2005. And we'll plug our research group as well. We've recently published a review paper on the current research trends in bearingless motors. So in summary, bearings are the weakest link in motor technology, and magnetic levitation offers an opportunity to overcome the challenges of bearings, but you need to weigh whether it makes sense for your specific application based on the specific challenges that exist in today's magnetic levitation. The key benefits are an increase in reliability and lifetime, increase in efficiency, dynamic rotor dynamics, health monitoring, but challenges and opportunities for further development include using your newtons wisely, so increasing force density, not in the sense of new magnetic materials, but in the sense of appropriate use of the force so that you get the most out of your hardware. Coming up with new technology to decrease cost, and solving integratability issues. Thank you. I now open the floor for questions.